Yeah, thanks for the introduction. I'm Hou Juntang. I'm a computer scientist at the Lawrence Berkeley National Lab, and I think my background is a lot different from most of you guys. I'm mostly doing research in computer science, and joining the EQSIM project is mainly for helping the group to better utilize the data from data production to data analysis and visualization. So with this talk, I will talk about some different perspectives on how we perform the efficient I/O, how we store the large amount of data, and how do we analysis and perform visualizations on the large data. So I will first start to list a few challenges in the exascale error management. As you heard from talks from Dave and Arvind in the morning, the DOE now has exascale computing, exascale supercomputers already deployed. The first one is called Frontier. It is hosted in Oak Ridge National Laboratory, and it has a little over 1 terabyte flops. So that's 1 billion calculations per second. It's really fast, and most of the high flops comes from the GPU accelerators. So Frontier is one of them, and the second upcoming exascale supercomputer is Aurora, which will be hosted at Argonne, and that one will have two exaflops. So and then we have some of the earlier version of pre-exascale supercomputer called Perlmutter at NERSC that is just located up here at Lawrence Berkeley Lab. And so these are three current state-of-the-art supercomputers that has GPU accelerators. However, all three comes with different GPUs from different vendors. So Perlmutter has a NVIDIA GPU, and Frontier has AMD GPU, and Aurora has Intel GPU. So the different GPU architectures comes with different programming models, and that has been making it very difficult for us to run our simulations on different supercomputers. Luckily, we have utilized existing software such as Raja to help us run our code, mainly SW4, with really minimal changes when we run it on different supercomputers. So that's one of the challenges. And now with all the GPU accelerated, we get really high flops. We can do a lot of computations in a very short amount of time, and that also generates a lot of data. And a lot of data, I mean, is really a lot. I can give you some examples. So for example, Arvind mentioned that we are doing the 5 Hz San Francisco Bay Area Hayward fault simulations with VS mean of 250 meters per second. So with one run, just one run, and if we are only talking about the surface data, so we have 120 kilometers by 80 kilometers domain, and the surface grid size is 6.25 meters. So we have a large number of grid points, and for each run, we will run for 90-second simulation time. That's hundreds of thousand time steps, and each run will generate over 200 terabytes of data. We are just talking about the surface data. If we want to output more data like the near surface with steps, then that's even more. So we are talking about even petabyte, one or 2 petabytes of data per run. So with this kind of volume, it's obviously we need some kind of data reduction technologies. Otherwise, we cannot utilize the data. It will take hours or even days to just open the data and read maybe just one time history. So next challenges is the sharing of the data. So Dave mentioned earlier today that we do our large runs on Frontier, and we do the analysis and visualizations on Perlmutter. So with the amount of data generated by the simulations, we need to transfer the data from one location to another, both the data and also the metadata that comes with the simulations. And last but not least, there is a challenge with this huge amount of data, and we are looking at multiple simulation runs. So there's a multiple factor. We want to also look at how can we provide easy-to-use data search and access interfaces. So I will go a little more into the details on how we are currently working towards addressing these challenges. So first, a brief introduction. I think Dave also mentioned in this slide. So the data management in our EQSIM workflow is we run the simulations at one supercomputing facility to generate the ground motions that the size can be easily hundreds of terabytes or even petabytes. Then we usually transfer the data through ESNet over to Perlmutter for the data analysis and visualization tasks. And then in the end, we will provide visualization and interactive interrogation of the large data size. And we provide an interface like an interactive map, which I will have hopefully working demo in the later part of my presentation. So as Dave and others also mentioned, in our project, we used HDF5 as a central role for managing all the data. So a brief introduction about HDF5. So HDF5 stands for Hierarchical Data Format version 5. It is a data model. It also is a software library, and it also includes a file format for managing large and complex scientific data. So there are a lot of good features about HDF5, but I will talk about some of the important ones that we value the most when using HDF5 in our EQSIM workflow. Another note is about HDF5 itself. It has just passed its 25th year. So HDF5 version 1 was released 25 years ago. And one good thing about this software is throughout the 25 years, it maintained the backward compatibility. So even we are using the latest HDF5 software, we can still open and access the HDF5 generated 25 years ago. And the main thing with HDF5 as a format is it is a self-describing format, meaning we can store both the data and the metadata inside one single file. And as the name suggests, there's the word of hierarchical. So inside the file, there's a type of hierarchy. So a file can be divided into groups, and groups can have subgroups. That's similar to the concept in the Windows or Mac OS, the directory or folder hierarchy. And we can maintain this hierarchy nicely with an HDF5 file, so we can group things into HDF5 groups, and then we inside each group we can have both the actual data as data sets and the metadata as attributes. So in the integration of HDF5 in the EQSIM workflow involves in many parts. So with pre-run, we have converted our existing input files such as the velocity model and the rupture sources into the HDF5 format. This is mainly in the consideration of running large simulations on supercomputers. So HDF5 provides a fast parallel I/O capability that helps us using minimum coding efforts and achieve very good performance with very large-scale runs. For example, on Frontier, the largest run we have uses more than 6,000 nodes, and each node comes with 8 GPUs. So with that large scale, I/O can easily be an issue. I will show some examples in my later slides to demonstrate that. And then after the input file, the simulation code produces many ground motion output files. So we have we usually output two main types of time history. One is used for the weakly coupled simulation. So we usually output the ground motions at a 2 kilometer spacing on the surface. And then we also have the option to output near surface volume data. So 3D volume plus time and writing to a HDF5 file. And once those files are written, they may be used for different analysis purposes. One example is for building response simulations. So we see the applying the motions to a building and see how the building reacts. And then we can also generate a map of showing how the hazards and risks distribute across the domain. So some minor details about the HDF5 format. So we have developed something called IceFile that stores the velocity model. This is very similar to the Brett Agard's GeoModel GRIS format. So we developed things to represent the velocity model around the same time, but now the IceW4 can read both an S file, which is HDF5 format. It can also read the USGS GeoModel GRIS data natively. So the next thing is the R-Band's rupture source file. So R-Band usually generates very large source files for us. So some of them can have millions of sources. And the original SRF format is really not good at handling those many sources with a text-based format. So to make it more efficient or more HPC friendly, we converted the existing SRF format into an HDF5 format. We did make many, we keep the original schema of the SRF format. It's just really converting the text into binary data, and the binary data is more efficient for HPC usage. And the converted data is about 1/3 the size of the text SRF file, and it can have more than 5x speed up. So then comes to talking about handling the outputs from the large-scale simulations. So I'm reusing one of Dave's slides, just showing the two options we have. Option one is outputting ground motions at a fixed 2 kilometer spacing, and option two is we can output near-surface volume data. And for option one, for a typical San Francisco Bay Area Haverford simulation with a domain of 120 kilometers by 80 kilometers, we are getting about 2.2 gigabytes data per simulation run. And with option two, the near surface, when we keep all the grid points just on the surface, we use compression, which I will explain a little bit in the next few slides. That one comes at a storage space of around 200 gigabytes. So for the first option, in SW4, we currently support 3 different formats. So those 3 different formats are really 3 options depending on how users are familiar with that. But one thing I want to point out is that for HPC or for large-scale runs, we should really look at least for the efficiency of writing the output files, the HDF5 format or even just the binary format will be usually much faster and more realistic to not result in a large amount of I/O time. So next one is the option two, where we output the 3D surface. So as I mentioned, it's a HDF5 format, and all the data is stored as a binary arrays. And we output usually velocity motions in the XYZ or for normal, for parallel and vertical directions. And combined with time is a 40 data sets. So we have 3 40 data sets within this one HDF5 file per simulation. And we do have support downsample in time. That is also one data reduction method we use, because otherwise there's even more data that we simply cannot manage. And as I mentioned, the San Francisco Bay Area simulations generate 200 to 300 gigabytes, and this is after downsampling and a factor of 100 of compression ratio. So talking about compression ratio, we switch to the compression mainly because the data generated by the simulations are just too large. And without the significant data reduction with compression, we can simply we don't have the storage space, or we cannot pass the data to anyone for any practical use. So we mainly look at the lossy compression. So I think most people are familiar with lossless compression, where you keep the original data resolution. When you compress the data and decompress the data, you get the same data. But the lossless compression generally cannot achieve very high compression ratio. Even the most optimized ones, you will probably get a ratio of 2. So you reduce the data size by half. That's the very optimistic case. Most likely you will get 20%, 30% reduction. And that is simply not enough for our use cases. So then we turn to the lossy compression. So different from the lossy compression, you lose some precision, but the new lossy compression libraries, they are usually provided error-bounded guarantee. So error-bounded means you can specify a precision where the lossy compressor will guarantee that after the decompression, the delta of the decompressed value compared with your original value is smaller than the threshold you specify as the error bound. So one nice thing about HDF5 is HDF5 supports transparent utilization of different compressors. So we chose CFP, which is developed at the Lawrence Livermore lab, and we found it compresses the data really well. So in this case, on the right-hand side, I have, this is from one simulation. So if we don't compress the data, we output the entire surface, it will generate a 76 terabytes file. And if we do use a lossy compressor of CFP, we are only getting 293 gigabytes. So we are getting a really high compression ratio. And another, the bottom right figure shows how well the compressed data compares with the original data. So it's only when we zoom to see the tiny details can we tell the difference. Otherwise, just looking at this velocity time history, there's really minimum differences. And also a nice thing about HDF5 is you can use the data as if it is not compressed. So in this example with Python, you can just import a module and then you can read the data as if it is not compressed. The HDF5 library will automatically cause the decompression, cause the compressor to decompress the data, and you get the decompressed values immediately. So I will skip over this. This is just to show there are some I/O performance tuning opportunities where if there can only really be a big difference when performing parallel I/O at large scale. And this is one example we did recently. We run a 10 Hertz simulation on Frontier with 2048 nodes. And overall, it takes 28 hours to run. And with our optimized I/O capabilities, the I/O time is only less than 1 hour. So our ideal goal is spend as little time as possible on the I/O part and to fully utilize all the GPU accelerators on the supercomputers. And next, I think I still have some time. I will do a demo of the visualization tools we have developed called EQSimWiz. Dave also mentioned that. And with lab demo, I hope things work. Yeah, so one little disclaimer about this is all the data is for illustration purposes. So I'm just trying to show the different capabilities of this EQSimWiz tool. The starting page is this. So we have a movie for the surface motions. Dave also showed this. It's just that we can put this movie into a Google Map, and then we can zoom in and zoom out to see the details, and can play and pause. So this is the animation, and we can also show a rough trace of the Haber fault on the map. And then is the more important thing. So as I mentioned, we have the output for the 2 kilometers spacing motions for the surface. So in this map, we can show all the about 2,300 stations. And if we zoom in, we can see they are all 2 kilometer spacing. And we can click each of this marker, and it will pop up a window to show the velocity history. So we have for parallel, for normal, vertical, and then we also calculated the displacement and acceleration. And we also have some metadata if you want to check what's the VS30 and the distances to the fault. We can all see that in this pop-up window, and you can open multiple ones to compare and see how things look like. Just I think this is really useful if you are a visual person and like to compare things visually, and you can open different windows to show to check whether there's any abnormality in any of the recordings. And then we have some filtering, predefined filtering to show a selection. So for example, if you are only interested in locations with acceleration larger than 1g, then you can click here and it will show all those locations. Similarly, there's an option to show stations where that has motions of over 2g. And we also have the capability to show the PGA, PGV map. So this is showing the horizontal PGAs. And you can combine this to find a place where there's high acceleration values, and then you turn on the markers for different locations, and then you can check that this place indeed have high accelerations, and you can compare with a place with low acceleration stations. Yeah, so I think this is really a convenient tool just for visually inspecting the motions from a simulation. Yeah, and that concludes my presentation. Thank you.